few that are power rule type questions where we've got an x, maybe a coefficient in front. And so in order to find the antiderivative, we add 1 to the power and divide by that new power. So this one right here is using the power rule. As is the integral of x to the 45th dx. Add 1 to the power, divide by that new power. So all the ones that I'm boxing off right now are power rule type questions. So the integral of the 4th root of x dx, one thing that we might want to do there is to rewrite this guy as the integral of x to the 1/4 dx. And once we do that, then we can use the power rule just like the others where we add 1 to the power and then divide by the new power. In this case, dividing by the new power was dividing by 5/4, which is the same as multiplying by 4/5. So this one is also a power rule question, or power rule integral. All right, let's see. Here's another power rule. Again, the integral of 1 over square root of x. The 1 over root x can be rewritten as x to the -1/2. And so once you do that, then when you add 1 to the power and divide by the new power, you get 2x to the +1. Okay, so that's another power rule. The final power rule, one that I want to focus on, is this one that looks like the integral of 352 dx. And then there's a separate one that's the integral of 352 dt. And the reason I want to focus on these two is that without that dx at the end, or without the dt at the end, we have no idea what variable will be placed on our number. So our antiderivative of a constant is that constant with whatever variable we're interested in tacked on the end. And so that dx or the dt is super important in terms of focusing on what are we taking the antiderivative with respect to. So there are more power rule questions. All right. Did I miss any power rule questions? This one down here? Yeah, this is a good power rule question also. So this one, the integral of 1 over x to the 4th dx, the very first thing I would do is to rewrite 1 over x to the 4th as x to the -4th. So the integral of x to the -4th dx, and then add 1 to the power and divide by the new power. So there is another power rule. And one more where we have a constant, and we're going to tack the variable onto our constant. Okay, are there any questions about the power rule? One integral that I did not box off in red, it almost looks like a power rule, but it is not, is the 75 over x. When I first look at this one, I might think to myself, oh, I see an x, and I'm going to rewrite it. It's in the denominator. I'm going to rewrite it as a power, so I have the integral of 75 x to the -1 dx. And so if I'm just sort of thinking willy-nilly about the power rule, I'd add 1 to the power and divide by that new power, and suddenly the world is exploding, and because we're dividing by 0, and so I immediately scratch my head and say, wait a second, I did something wrong. And the thing that went wrong here was that the power rule, the integral of x to the n dx, is x raised to the n plus 1 divided by n plus 1 plus c, as long as n is not equal to -1. And in that case, we have that special case where the antiderivative of 1 over x is natural log of the absolute value of x. So this guy right here is a special case. Now, the 75 gets pulled along because we can pull that 75 out to the front, then take the antiderivative of 1 over x dx. Okay, so that's our natural log. I don't see any other. Oh, there's another natural log over here. This is the basic one. All right, so natural log. So the antiderivative of 1 over x is natural log. Related to that is e to the x. And so the antiderivative of e to the x dx is e to the x plus c. And what we have left are some trig functions and some inverse trig functions. In Calc 1, you hopefully derived or came up with the derivative of arc sine as 1 over root 1 minus x squared. And so this is an antiderivative to just identify and say, oh, when I see 1 over root 1 minus x squared, its antiderivative is arc sine. Let's see what color should we use now? How about blue? So inverse trig functions. We also have the antiderivative of 1 over x squared plus 1 is arctangent. Those are the two main inverse trig. And what is left over are our regular trig functions, antiderivative of sine, antiderivative of cosine. Some that are good to just identify are things like, we know that the derivative of tangent is secant squared, so working backwards, the antiderivative of secant squared is tangent. Same with antiderivative of cosecant cotangent, antiderivative of cosecant squared, and antiderivative of secant x tangent x. Okay, so these are the antiderivatives that hopefully look relatively familiar to you. And if they don't, or if you don't feel comfortable with them yet, then what you should do is go back into your textbook, and there's a summary of these on page 277. So a summary of known indefinite integrals is on page 277. Okay, any questions or comments about any of these? Okay. So at this point, unless you were one of the unlucky folks who got stuck finding your other half of your slip of paper up here on the table and didn't have a partner, you should now have met at least 3 people in this class. So you should know 3 names, plus your own name, plus my name. So you should know a minimum of 5 names in this class at this point. Okay, so some other things that you did at the that you worked on in Calc 1. Earlier on in the semester, you talked about the chain rule. And so well before you took the gateway exam for finding derivatives, you learned about lots of different derivative rules, the quotient rule, the product rule, the power rule, and the chain rule. And so the chain rule from Calc 1, if you have a function f of x, and f of x is equal to 2 times the sine of x cubed plus 4x plus 8, and you were asked to calculate the derivative. Well, if you were asked to calculate the derivative, then you might look at this and say, okay, I see a trig function here, and nested within that trig function I see another function. So I've got a composition of functions, and I've got an inside function of x cubed plus 4x plus 8, so I've got 2 times the sine of stuff. And so I would need to use the chain rule. So what I'd like you to do now is I'd like you to take 30 seconds and write down on your paper what you believe the derivative is of 2 times the sine of x cubed plus 4x plus 8. even if you have not totally written your final answer down, turn to somebody near you and say hello.
Guten Tag.
Or in any language is fine. And share what you have with your neighbor. See if you agree.
Not totally sure.
Did you get it? Not yet. Yeah. Take your time. It's not a competition.
Okay. Does anybody have an answer that agrees with what your neighbor has? Wait, what? 11 is 2.
2 times 2.
Okay. Okay, does anybody else have this as a final answer? Okay, so this makes sense. So when I have a function that is a composition of functions, then I'm talking about an inside and an outside. And so in this case, my inside function is x cubed plus 4x plus 8. And my outside function is sine of x. And the 2 I'm going to carry along as a constant written in front, so it just comes along for the ride. So chain rule says, and there are many, many different ways to say the chain rule. The way that I usually say it is, the chain rule is the derivative of the outside, keeping the inside the same, times the derivative of the inside. And so in terms of my calculations, my derivative of sine x is cosine x, and my derivative of my inside, x cubed plus 4x plus 8, is 3x squared plus 4. So I've got derivative of the outside, cosine, keeping the inside the same, copying down x cubed plus 4x plus 8. So cosine of all the inside stuff times the derivative of the inside. So derivative of the inside is 3x squared plus 4. And that 3x squared plus 4 I need inside parentheses. Okay, so that's our chain rule. Any questions about that? Okay, great. So let's suppose then, you were walking down the street and out of this dark alley pops this integral. It throws itself up on the board and it says the integral of 6x squared plus 8 times the cosine of 4x cubed, I'm sorry, that's not a 4x cubed, just an x cubed, so x cubed plus 4x plus 8 dx. So you're just walking down the street and this integral pops out at you and says, here I am, evaluate me. And so you look at it and you say, well, I just so happen to have come out of my Calc 2 class where I was just reminded about the chain rule, and this looks an awful lot like, well, something that's written over here on the board. In particular, if I factor 2 out of this first part, then I have 3x squared plus 4, then times the cosine of x cubed plus 4x plus 8 dx. And so suddenly this part in the middle here looks an awful lot like the derivative that we came up with when we used the chain rule. And so to find the antiderivative of that thing in the middle there, I need to know what the original function was, and it just so happens to be written up here. And so the antiderivative of 2 times 3x squared plus 4 times the cosine of x cubed plus 4x plus 8 is 2 times the sine of x cubed plus 4x plus 8. And I need a plus c on this, because there could have been some constant that got lost in the shuffle. Okay, so this is great. If you just so happen to be talking about the chain rule in your calculus class, and you leave your calculus class, and an indefinite integral jumps out at you from a dark alley that you need to evaluate, and it just so happens to be a value that looks like, just like, a derivative that you just calculated, you can come up with the antiderivative. Okay, so that's great. Although not very useful. So in general, I mean, if you didn't happen to come right from calculus and you didn't happen to be thinking about this specific problem, how would you evaluate this indefinite integral? Well, the answer is that we're going to use U substitution, which is our technique for undoing a chain rule. So when we have an integrand where we've got somehow an inside function, and that inside function I can see its derivative or some form of its derivative showing up in the problem, then I want to think about using a U substitution. Now, what we're going to be talking about over the next few weeks are different techniques of integration. So the basic integrals that you wrote up on the board right before the break are integrals that you'll know and you'll be comfortable with. But there are about a bajillion other integrals that are not straightforward. And the goal of the first few weeks in Calculus 2 is to work on techniques to evaluate these indefinite integrals, and sometimes definite integrals, that are more challenging than the ones you saw in Calc 1. So as I start to talk about these indefinite integrals, I'm going to be throwing out some strategies, and so hopefully you'll start to absorb some of these keys that I'm throwing out there. And even though right now we'll know U substitution, throughout the next few weeks we're going to add on some other techniques. So even though we only have one choice right now, this idea of U subs, well, later we're going to have more. And so I want to get into the practice of identifying and looking at the integral and saying, U substitution is a good idea. And U substitution is a good idea because I see an inside function, and I see some sort of the derivative of that inside function up here. Okay, so I want to think, okay, U sub. All right, so U substitution. So if we don't already have an antiderivative in mind, we might try U subs or U substitution. All right, so I'm going to work through this one, and again, hopefully you saw this in Calc 1, but this is where we're starting here in Calc 2 as well. So I've got 6x squared plus 8. So the integral, or the antiderivative of 6x squared plus 8 times the cosine of x cubed plus 4x plus 8 dx. And I immediately identify that I've got an inside function sort of nested in there, and somewhere else in this problem is the derivative of that inside function. So I'm thinking, okay, U substitution. So I'm going to let U be that function that's on the inside, the inside nest of our function. So U is equal to x cubed plus 4x plus 8. Now, there are a variety of ways of working on these U substitutions, and so your technique for doing this intermediate part may be different than what I'm doing, and that's okay. And if you prefer your way, please keep doing it, and if you feel that your way is different and you're not sure if it really is going to work, you can ask. Okay? So I'm just presenting one way to do a U substitution for now, and if you have other ways and you want to talk about them, please ask. Okay, so we're going to let U be equal to x cubed plus 4x plus 8, because that's our most inside function, and I see its derivative showing up here. All right, so some extra work on the side here, besides knowing what my choice for U is. I will need to take the derivative of this equation, so I'm going to take the derivative of the left side, and I have du over dx. And the derivative on the right side will be 3x squared plus 4.
Yes.
So I actually wrote it as du over dx, so if you write it as du equals blah dx, also works.
Okay.
Alright, so I'm going to make some substitutions. I'm going to substitute u for the x cubed plus 4x plus 8. And I'm also going to replace dx. So I need to solve this equation over here for dx. So I'll multiply both sides by dx. And then divide both sides by 3x squared plus 4. So in the end, I've got that dx is equal to du over 3x squared plus 4. So those are the two pieces of information, the two pieces that I'll need to continue working on my problem. Okay, so now back to the original integral. We've got the integral of 6x squared plus 8 times cosine of u, and the dx I'm going to replace with du over 3x squared plus 4. All right, now at this point, I'm in a very sensitive and precarious position. Okay? I started out with an integral all in terms of x's. My goal is to turn my integral entirely into the variable u. Right now, I'm halfway in between. This is a very poor place to be. If you ever owned a transformer in your life, you know that that transformer is better suited either the vehicle or the robot, but if you're halfway in between, you can't do anything with it. Okay? And so right now we can do nothing with this. So I look at it and I ask myself, can I cancel out all of those x's? I'd like to get rid of the x's. And the answer is yes, but how can I do that?
Do you factor the 2 and then just cancel them?
Yeah, so these nearly look alike, and it would be nice if I could cancel them. In order to do that, I've got to factor out that 2. So I've got 2 times 3x squared plus 4 times cosine of u times du over 3x squared plus 4. And now, very nicely and very happily, all of my x's cancel, and I am left with the integral of 2 cosine u du. So at this point I'm very happy. I've completely transformed my indefinite integral into variables with u. If I get to this point and I still have x's left over, something went wrong, okay? Or I need to be more clever, okay? But I must have all u's and no x's. And the whole point of doing that is now I can take an antiderivative. I sure didn't know what the antiderivative of this ugly mess was, but I know what the antiderivative of cosine of u is. The antiderivative is sine of u, and that 2 will get carried along. It's a constant in front. And then I've got my plus c, because it is an indefinite integral, and I didn't know about whether I had a constant on the original function before its derivative was taken. And at this point, I am 99% done. Yeah, so at this point, I have an almost complete answer, except my question was asked in terms of x's, so my answer must be in terms of x's. And so we have 2 times the sine of u, but u was x cubed plus 4x plus 8. And so my final answer, 2 times the sine of x cubed plus 4x plus 8, and parentheses plus 12. All right, are there any questions about that? Yes, Maggie.
How can you drop the du for that last step?
This step right here? So the du and the integral sign are telling me take the antiderivative of the thing in the middle, and once I do that, that's when I drop both the integral sign and the du. Okay, other
You're just
questions?
you're just trying to get it to the u, and then you take your antiderivative.
That's correct.
Plug in your u and just make sure you see it.
That's correct. Yep. Yep, so the main goals are transform your integral into u's, and hopefully that is an integral that you can find the antiderivative. Turn it into u's, take your antiderivative, return back into x's. Okay, other questions? Okay? All right then. All right, let's take a look at a second example. In this example, we have the integral of this indefinite integral, what I see up here is something fancier than just x raised to the third. If I just saw an x raised to the third, then I could use my power rule, add 1 to the power divided by the new power. But here, I have something fancier inside. And so I'm kind of identifying an inside portion of this function. And so I'm thinking maybe I've got a u substitution going on here, and I would let u be that inside portion, the 4x plus 3. Now as I start to think ahead, I want to think ahead and think, okay, if this is my u, and I quickly think to myself, what is its derivative? Its derivative is 4. And I look over here, once I turn this into u, there are not going to be any x's left over. So my derivative doesn't need to cancel anything, and that's good. Okay? So I kind of think that ahead. I think ahead with that in my mind, but then I do the work as well. And so I've got u is equal to 4x plus 3. My derivative, du over dx, is 4. And my work on the side over here, I'm going to solve this equation for dx. So an intermediate step is to multiply both sides by dx, and then divide both sides by 4. And finally, dx will be equal to du over 4. Now, I mean, 100% of the time, you're going to take this du over dx equals your derivative, and to solve that, you're going to end up with dx is equal to du